When choosing the enzymes for a biosynthetic pathway, it is not only the sequence of intermediates that determines the efficiency of the device. For example, the enzymes might express poorly or be toxic to the cell. Additionally, subtle differences in substrate preference and the kinetics of each step can have dramatic effects on productivity. In this butanol biosynthesis study, Chang and co-workers examine hybrid butanol pathways and identify more efficient routes by careful consideration of the substrate specificity of each enzyme and the thermodynamic parameters of each step. The most common route to N-butanol is based on the Clostridium pathway for butyric acid. This route starts with acetyl-CoA but goes through this alcohol intermediate. They noted that a similar sequence of intermediates were produced during this 3-enzyme polyhydroxybutyrate pathway from Ralstonia eutrophis. If they only took Fa-A and Fa-B from this pathway, they'd reach the 3-hydroxybutyryl-CoA intermediate also in the Clostridium-based butanol pathway. Thus, by combining these two genes with the downstream genes from the Clostridium-derived path, they'd reconstitute a very similar pathway to N-butanol. This was the first hybrid pathway they described, called Bu1. Through a series of observations, they conclude that CCR is the slow step in their pathway. Thus, there is a bottleneck at crotonal-CoA that limits butanol production. They also note that the reduction step is reversible. Closer inspection of the biochemistry of this enzyme and alternates reveal that most enzymes one might choose for this reduction step employ a flavin mediator. The free energy for reduction with a flavin is closer to zero than reduction with NADPH. Thus, if they use an enzyme that was entirely flavin independent, this step might be irreversible. They identify such an enzyme from treponema called TIR and swap out CCR with it. When they exchange TIR for CCR, the Bu1 combination of Fa-A, Fa-B, and CRT, the topmost route in this figure, they observe poor yield and investigate alternative genes at the reduction and dehydration steps. For the NADH reduction step encoded by Fa-B, they could use the Clostridium enzyme in red, HBD, or the Ralstonia enzyme, Fa-B, in blue. Similarly, in the subsequent elimination step, they could use either source organism with CRT or Fa-J, respectively. They find that only the Bu2 and Bu3 combinations, the middle two routes in the figure, give high yield. The explanation for the difference deals with the subtle aspects of enzyme specificity. Fa-B and HBD reduce acetyl-CoA from opposite sides of the molecule. Fa-B produces the R enantiomer and HBD produces the S. In the next step, dehydration of the alcohol to an alkene can result in the cis or trans isomer. Fa-J only accepts the R enantiomer and generates the trans product, while CRT will accept either intermediate and generate cis or trans based on the stereochemistry of the alcohol. The next step, reduction with TIR, only works for the trans intermediate. Thus, combination of HBD and Fa-J results in no product. If you use CRT with the R intermediate, the alkene intermediate is formed, but it is not a substrate for TIR. By virtue of these subtle differences in substrate preference, dramatic differences in production rates are observed for the 4 different combinations. The off-species combinations give poor yield, and the on-species ones produce comparable high yield. This paper demonstrates how very subtle differences in substrate specificity and the free energy of critical steps can dramatically affect the productivity of a pathway.